Okay, so we are again doing curve sketching. Curve sketching 2. Okay. Now, we want to first look at slant asymptotes. Sometimes instead of slant, we use oblique asymptotes. The general idea is this one. Idea for an asymptote. Okay, we have a function. Okay, so f of x, we can write f of x, say, as f1 of x plus f2 of x. This is general theory, so it doesn't make sense until it is over, such that limit as x goes to infinity of f2 of x is 0. Okay, then the graph of y equals f of x is asymptotically close to the graph of y equals f1 of x as x becomes larger. Okay, so we say y equals f1x is asymptote to y equals f of x. Okay, if f1x is linear, that is of the form ax plus b, then we call it slant or oblique asymptote. Okay, so that's the general idea of understanding asymptotes. You look at the expression for this, you pull out something which goes to 0 as x goes to as x goes to infinity. Okay, so you try to take as many pieces as you can into this part, so that when x becomes large, it becomes 0. Here you obtain an expression. When x goes to infinity, this probably also goes to infinity. Okay. Then this is your asymptote. Sorry, what we did last hour is, again, we did this, but this part was, if you play around with it correctly, this part was a number. Okay, here a was 0 and f1 was just b. So here we say a is different than 0. If a is 0, then that's a horizontal asymptote. Okay, so that's the definition. Let's look at some examples here, and then I'll do some curve sketching with interesting functions. Well, the functions must be interesting and doable. Okay, so examples are y equals this one. So f of x is equal to x squared over x plus 1. Okay, so as x goes to infinity, this goes to infinity, that part that we can understand. Okay, as x goes to minus infinity, this goes to minus infinity, right? First of all, let us do those things. So limit x goes to plus infinity, x squared over x plus 1. So this is, so let me write it this one now to make it clear. X goes to infinity, I have x times x over x plus 1. Okay, as x goes to infinity, this goes to 1, right? And this goes to plus infinity. So if I take x going to minus infinity, this will be minus infinite. But this part is again going to be 1. Okay, so So this is equal to plus infinite, since limit as x goes to infinite, x over x plus 1 is 1. If we do this with the negative 1, minus infinite, x squared over x plus 1, this is limit as x goes to minus infinity, x times x over x plus 1, but this is now minus infinite, again for the same reason. That part doesn't contribute to the sign, the limit is plus 1. Okay, so our graph comes from minus infinity, goes to minus infinity. It is 0 at x equals 0. It is undefined at x equals minus 1. Okay. So let us try to play this game. Okay, x squared is a polynomial, x plus 1 is a polynomial of a smaller degree, so we divide it by that. Either you do long division or you do the usual old trick in mathematics, you add or subtract something, x plus 1. So I subtract 1 and add 1 to this. I have x plus 1. Okay, so this thing is x minus 1, x plus 1, plus 1. I'm dividing it x plus 1. Okay, so this is going to be x minus 1 plus 1 over x plus 1. Okay, so you see I managed to write f as f1 plus f2. This part goes to 0 as x goes to infinite. Okay, I'm not taking the limit of all of this. I'm looking at them separately now. This part goes to infinite, to 0 as x goes to infinite. So when x is very, very large, this will be negligible. The function will behave like this one. Okay, so that's the basic idea of an asymptote. Asymptote, you expect an asymptote to have a simpler expression, and you want your function to behave like the asymptote when x is very, very large. Okay, so this is exactly what happens here. Then, since limit x goes to infinity, well, actually plus or minus infinite in this case, 1 over x plus 1 is equal to 0. Y equals x minus 1 is the slant asymptote for this function, for this graph. Okay, so what do we expect? So we expect okay, by looking at this function, we know that at x equals minus 1, it's not defined. So we have this thing here. This is minus 1. The function is not defined here. And this is our asymptote. So y equals x minus 1 means when x is 1, it is 0. So we have this thing. This is y equals x minus 1. And the function will pass from here. So I think I did this example in detail. Let me check. If not, here it is. Okay, so okay, so you see our function f of x is equal to this asymptote plus this number. When x is positive, when x is on this side, 1 over x plus 1 is positive. Okay, so the graph should be above this, above the asymptote here. Okay, and here on this side, when x is less than minus 1, this is negative, and you take this graph, the asymptote, and you subtract something, so the curve is here. Okay, so the curve is here. So we expect something like this and something like this. So let us check if this is really going to be the case. Okay, so now we did this part. We checked the behavior of the function at the endpoints. It goes to infinity. Okay, it goes to plus infinity here. It goes to minus infinity here. We found the asymptote. So these things we did without using the derivative. So time has come to do the derivative. So f of f, okay, I called it f. So f prime x is equal to, so I'm writing the simplified form here. X plus 2 over x plus 1 square. Okay. And I also calculate the second derivative and simplify it, and it is 1 plus x cubed. Okay. So I prepare the table that I mentioned last hour. So x. So how many? Okay, so I need this much. So this is f prime. I also want to see the size of f double prime. Okay, so I think that's enough. So when x goes to minus infinity, we found that f goes to minus infinity. When x goes to plus infinity, our function is going to plus infinity. The function is not defined at minus 1. Okay, so this is, remember, this is the universal sign we use to denote that these things are not defined there. At x equals minus 2, there is something happening. The first derivative is 0. And at 0, the function is 0. Okay, so maybe I remind ourselves what the function was. This is x squared over x plus 1. Okay, so that's where the function is 0. And since we have an asymptote, we have to check the limits also. Okay, so here we check limit as x goes to minus 1 from below f of x. Okay. This is always positive. This is going to be 0, so we expect plus or minus infinite in the limit. If x is less than minus 1, meaning that the absolute value of x is larger than 1, okay, but it is negative, so x plus 1 is going to be negative. Okay, so at every step before minus 1, you get a negative number here, and when this thing approaches to 0, you go to minus infinite. Minus infinite. And you look at limit, x goes to minus 1 from above, f of x. So the same argument this time. X is larger than minus 1, so x plus 1 is positive, but going to 0. This is always positive, okay, and it's not going to 0. So this thing is becoming infinite, and the sign is plus. Plus infinite. Okay, so here, going to this is minus infinite here and plus infinite here. So we check this with our expectation. Okay, so the function comes from minus infinite, changes its mind, and again goes to minus infinite. And here, again, the same thing happens. Okay, same thing according to our expectation. It comes from plus infinite, goes to plus infinite. Okay, now next we examine the sign of f prime. Okay, so we look at this thing. Suppose everything is smaller than minus 2. This is negative, so this is plus. Okay, so here it is 0, and here, now in between minus 2 and minus 1, this is negative, but now this is positive, so this is negative. And here, between minus 1 and 0, this is negative, but this is positive because x plus 2 is large. So we have negative here. And from 0 on, these are all positive, so everything is positive. And at f prime is also 0 here. We forgot to put that. Okay, so f prime is 0 here and here. Okay, so we again check this with our expectation. It is increasing, has a local maximum, goes down, and then comes from minus infinite, has a minimum, and then goes up. And since this is a local minimum, and at that local minimum the function is itself 0, the graph doesn't go below x-axis. It touches x-axis and then goes up. Okay, so far so good. Let us look at the sign of the second derivative. Okay, so this part is easy. This is positive always. So since this is a cube, the sign of f double prime will be determined by the sign of 1 plus x. 1 plus x is negative if x is less than minus 1. So it is all negative here. And it is positive if x is larger than minus 1. So it is all positive here. So this says that the graph is concave down. Okay, in our expectation it is like that. And this says it is concave up. Okay, so that's what's happening. And this one tells me increasing, decreasing, and decreasing, increasing. I do put these symbols by looking at this. Okay, so the last step is to plot the graph, but our expectation was correct. There is no need to modify. The only thing here would be maybe we would take this down here and take it up, but then that would tell us that x equals 0 is a local minimum, so it doesn't go down. So our first expectation was correct. Well, actually, I would normally take this down like this, but somehow I remembered this because I did it last night. So, okay. So this is a typical procedure to curve sketching from infinity to infinity. Okay, let's do another one, but first let me check if there is something else on the agenda. Okay, so we do these things. So, okay. So let me do another graph. Okay, so our second graph is f of x equals x squared minus 4 over x squared minus 2x. Okay, so first of all, observe that I cannot put x equals 0. So the function is not defined at x equals 0. And, okay, let's see, maybe I cannot put x equals 2. Okay, at x equals 2, the function will be undefined. So here we know that x is different than 0 and different than 2. Okay, so this is the function given to us, or we were working on something. That something doesn't make sense when the parameter is equal to 0 or 2, and we want to sketch its graph. Now, first, of course, you see that there's lots of cancellation here. So first, simplify f. Okay, so f of x is equal to x minus 2, x plus 2, right? And here I take out x, and I have x minus 2. Okay, since x is never 2 in my problem, I can cancel these out. I have x plus 2 over x. Okay, and of course, now I can write this as 1 plus 2 over x. Okay, x is different than 2 in my problem. So x minus 2 is different than 0 and can be simplified. If you are sending this solution to someone, you must put this explanation, okay, because the other person may jump up and say, what if you are canceling zeros? Okay, so you are not canceling zeros. And suddenly this also gives me the asymptote. You see, I managed to write f of x as something plus something. The other something goes to 0 as x goes to infinity. So the function behaves like this when x is very large, either plus going to plus infinite or minus infinite. So this becomes the horizontal asymptote. So here we see that y equals 1 is the horizontal asymptote. Okay, so the curve is approaching to that. When x is positive, when we are going to plus infinite, this is positive. So you add something to the asymptote to obtain your function. The graph lies above the asymptote there. When x is negative, the graph lies below the asymptote. When x is 0, nothing is defined, so we don't know what happens at 0. Okay. Okay, so next we take the derivatives, of course, this being calculus. F prime x, so this is, well, this is easy. This is minus 2 over x squared. F double prime x is 4 over, well, this 2 comes here, 4 over x cube. Okay, so now we have all the information to prepare this table. Let us prepare this table x. So how many lines I have? 3 lines. Okay, so x, f prime, f double prime. When x goes to minus infinite, what happens to the function? No, after I get my answer. What's the limit of this as x goes to minus infinite? You are not answering because it is so trivial, or you are not answering because you don't know what happens. Which one? What's the limit of f of x as x goes to minus infinite? Why is there a question mark after 1? 1. This is f of x. X goes to minus infinite. This is 1. Okay, so let me extend this a little bit. Plus infinite, the same thing. Okay, so that's what we said here. This is the horizontal asymptote. Okay, so the important point is minus 2, 0, and 2. At 0, the function is not defined. At 2, the function is not defined. Okay, this expression is defined. Okay, but the function behaves like this expression when it is defined. We didn't define. This is modeling something that we are working on. And in our model, x equals 0 and 2 doesn't make sense. So we have to respect that in our graph. Okay, so f prime and at x equals 2, at x equals minus 2, my function is 0. Okay, so nothing else is 0. Okay, so I look at f prime. This is f prime. Okay, so you see that f prime is always negative, right? Negative, negative in all these things. And f double prime is x cubed. So it is negative when x is negative. Positive, it is positive. Okay, so that's it. Now I look at these things. The function is decreasing, decreasing, decreasing. The function keeps decreasing. Okay. So decreasing means that here we have these things. So let us look at what happens when x approaches to these undefined points. So when x approaching to here from left, so that is limit x approaches to 0 from left of f of x. Okay, so this is the limit I am taking. This becomes infinite, but sign of x is negative, so it becomes minus infinite. Okay, so this is minus infinite. And limit x approaching to 0 from the right is plus infinite. Okay, so here as x approaches 0, this is infinite, and the sign is plus. So here I have minus infinite, plus infinite. So I check if these arrows make sense. It decreases from 1 down to minus infinite. Okay, it makes sense. It decreases. Okay, so let us look at this this part also. Limit x approaches to 2 from the left of f of x is 2, right? But this is also the case if limit x approaches to 2 from the right. Okay, because this undefined point is an artificial undefined point. This is 2 in both cases. So the function decreases from plus infinity down to 2. For some reason, we don't want this value. And then it decreases from 2 to 1. Okay, so that makes sense. Let us check if we manage to find the concavities correctly. Here we found concave down, concave down. Okay, so this is how you go down. That fits. And here, concave up, concave up. Okay, so it goes down like this. So everything in this table makes sense. So the final thing is to plot this roughly to give an idea as a picture. So we have this x-axis, y-axis. We don't have anything at 0, and for some reason we don't like 2 either. So this is 2. So what happens at -2, the function will cross x-axis there. And I have the asymptote, horizontal asymptote. This is 1 here. Okay, so the function starts from 1 in the limit and goes down to minus infinity. I also checked that when x is negative, the curve stays below the horizontal asymptote. So, and it is concave down, so apparently it will be something like this. Okay. Coming to this side, it starts from plus infinity, goes down to 2, but on both sides it is 2. So it goes down to 1 and it is concave up. So the picture is this. So if this is 2, okay, so I'll do it like this. Okay, and this point, at this point, the function is not defined. Okay, so this is the curve. Okay, so it is asymptotic to this. So y equals f of x. It's not defined at 0, and at 2, it's, the formula does not give us any information, but we see that it just skips this point here and then continues again from that point. Okay, so you had a question.
Yeah, I understand.
You understand, okay? So it's nice to have bright students. You don't have to work hard. Okay, so another one, let's see. Okay, let's do this one. Buraya saat almadık bir türlü değil mi? Okay, so let's see. I have some interesting examples. Let's look at this one now. F of x equal to 2x cubed divided by x cubed plus 1. Okay, so you see that this is when x is different than -1, because at that point the function is not defined. So let us follow this. If something works, don't touch it, don't change it. Okay, so first simplify this. F of x, which is equal to 2x cubed over x cubed plus 1. Okay, so I added 2 to this and subtracted 2. Okay, so let me do I added 2 so that this thing is divisible by this and it will give us 2. Now I subtract 2, x cubed plus 1, and the result is 2 minus 2 over x cubed plus 1. Okay, so this gives us that horizontal asymptote y equals 2 is horizontal asymptote. Okay. And again, looking at the sign of these things, we know if it is above or below. If this part is positive, the curve is below 2, etc. Okay, so we'll do that when we come to plotting. Then we take the derivatives. Then derivatives. F prime x is 6x squared over x cubed plus 1 square. The second derivative is equal to 12x 1 minus 2x cubed over x cubed plus 1 cubed. Okay, so very easy. You write this to Maple or Wolfram, ask for the derivative, second derivative. If you don't like the answer, you say simplify the answer, and then you write this. And let us check the limits. Limits at infinity. So limit as x goes to, well, in this case, you see, it doesn't matter. We can take plus or minus infinity of f of x is what? What's the limit as x becomes larger and larger? 2. This is 2. Okay, so these behave the same. Okay, or divide everything by x cubed. You have 2 over 1 plus 1 over x cubed. This goes to 0. You have 2. Well, the easiest case is here. Take the limit as x goes to infinity. You have 2. So that's the meaning of horizontal asymptote. Okay. Okay, so the function, and so we'll eventually look at the limits around the vertical asymptote. X equals minus 1. Okay, so you see that we have a asymptote there. So limit f of x as x goes to minus 1 from below. Okay, so if x is around minus 1, 2x cubed is negative. X cubed is negative, but it is less than, x is less than 1. So its absolute value is larger than 1. So this is also negative. So negative over negative, this is positive. And what do we get? 1 or minus infinity? Plus infinity. 8. Pi over 3. Yes, what is the limit? This is the vertical asymptote, so we are expecting limit as 4. X, this is when x goes to minus infinity, the denominator goes to 0. The numerator does not go to 0. So we are expecting plus or minus infinity. Okay, to make sure that we catch the sign, we are approaching it from one side first and from the other side. When we are on this side of minus 1, this is negative. This is also negative. This is negative but going to 0. Okay, so the overall sign is plus, and it is increasing because the denominator is going to 0. So this is plus infinity. Okay, so let me write plus infinity. And limit as x goes to minus 1 from the right of f of x. Now again, around minus 1, this is negative. Very close to minus 1, this is negative, and it's not going to 0. But this time, this is positive because absolute value of x is less than 1, but it is negative and close to minus 1. So this whole thing is going to 0, but it is always positive. You are dividing negative by positive, and that positive is going to 0, so this is plus infinite. Minus infinite. Okay, so negative over plus is minus. Okay, so fortunately I found the same thing last night. Okay, so I think these are all the technical information we need to prepare our table. So we can, okay, so these things, the zeros of these I'll put on the table. So I have x, and I have again 3 points there. I have f, I have f prime, I have f double prime. At minus infinity and plus infinity, I know that 2 is a horizontal asymptote, so here I'll have 2. At minus 1, nothing is defined, but I have the limits. On this side, the function goes to plus infinity. On this side, the function comes from minus infinity. I have 0. At 0, the function is 0. The derivative is 0. The second derivative is 0. So everybody sleeps here. And I have 0.8, well, approximately 0.8. That's the root of this, cube root of 1 over 2. It is 0.79 something, so I wrote 7.8. Okay, so this is 1 over 2 cube root. Okay, so what happens here? The second derivative is 0. Okay. So now let us look at the sign of f prime. Sign of f prime is positive. Okay, square over square is always positive. So this function is relentlessly increasing. And the sign of second derivative, okay, so let me just write what I found last night. Okay. So you see here you have to consider 3 things: the sign of x, the sign of this part, and the sign of the denominator. Okay, so you put these things together, you get these signs. So the function is increasing. The function is always increasing. It is concave up, concave down, concave up, concave down. Okay, so let us now plot this. So let me see, I need everything. X, Y. Here I have a horizontal asymptote. So this is 2. I have a vertical asymptote, not to scale. Okay, if this is 1, then 2 must be here. But you don't get scaled graphs in software either. Okay, so this says the function starts from 2 and goes to infinity. And by looking at here, when x is very negative, this part is negative. You have another negative here. So this part is positive. You are adding something to 2. So the graph remains above 2 all the time. And it goes like this. It goes to plus infinity. And it is concave up. So this side is like this. Okay, so the function is coming from minus infinite, cutting the x-axis here at the origin, and then it continues to increase but changes concavity, and then here it changes concavity and becomes asymptote. Okay, so that point is somewhere here, so the graph is something like this. The derivative is 0 here, so this comes like this, it touches x-axis. You see somewhere here it changes concavity and becomes like this. So somewhere here, this is 1 over 2 cube root at this point, inflection point. Okay. Here you can also check for oh, sorry. You can also check from the expression here that the graph must remain under 2 because you are subtracting something from 2. It is also clear from here because the function is continuously increasing. If it ever crosses x-axis, then it must increase. It cannot come down asymptotically to y equals 2 line. Okay, so the graph makes sense. And at this point, we believe that it is correct. Okay? So this is how the function is behaving. Okay? Any questions so far? Okay, let me find another example. Okay, so I have two examples. The last one I'll just mention because that's a nice exercise from the book. Okay, so this time we don't have any asymptotes. This is say for f of x is equal to a polynomial 2x cubed minus 9x squared plus 12x minus 5. Okay, so this one, first you have to find the roots. Okay, so if a cubic equation has to be solved as an exercise or as an exam problem, it means that the roots are 0, plus or minus 1, or plus or minus 2. Okay, the roots must be obvious. Otherwise, the routine to find the roots of a cubic polynomial is very long. Look it up in Wikipedia, Cardano formulas. Okay, now we take the derivative f prime x is equal to 6x squared minus 18x plus 12. That also factors as 6, x minus 1, x minus 2. We also need the second derivative for concavity. This is 12x minus 18. That also factors as 6 times 2x minus 3. Okay. And the graph will be, okay, so prepare something like this. You see now, once I have this part, the signs are very easy. The limits are also easy. Since this is x cubed, it comes from minus infinity, goes to plus infinity. So the graph will be something like this. Okay, so it goes like this, touches x-axis somewhere, comes down. So you see it's all concave down, and somewhere here it changes concavity and goes like this. Okay, so we know the points. This is 1. Okay, it's a double root, so it touches there, it doesn't cross it. And this point is again from here is what, 5 over 2. Okay. And this point from here is 3 over 2. 3 over 2, inflection point. Okay, so the rest of the curve is clear. Okay, now the last thing I want to mention is an example from the book. Okay, so let me patiently write this. Now for these examples, you just give the curve, the equation to a software. You say plot this, it gives you exactly these curves. Okay, so that's your expectation. You look at the graph, the software gives you this graph, of course without these dotted lines, etc., but you understand what's happening. Okay, so you develop your expectation. But with this one, you don't get any expectation because the numbers are strange. 3x squared plus 500x. Okay, so this is cube x squared over x cube plus 500 x squared plus 100x plus 2000. Okay, so if you give this to the software and you say plot this so that I get an expectation, this is what you get. Okay, so software will give you this one. Okay. However, if you follow this procedure, you will see that the curve looks something like this. So, or it says software Of course, this is not the fault of the software because you just give the formula, you say plot this. So the software plots this in a reasonable interval around 0. Okay? So if you give more detailed expression instructions, the software will obviously give you the precise curve. Okay? So, but what happens is the actual curve after the usual procedure, after doing these things. Of course, you do these things again with the software. Who wants to take the derivative of this and simplify it by hand? You ask the computer to calculate the derivative of it, finds its root, second derivative finds its root, then you prepare the table. When you prepare the table and plot, you will get something like this. So let's see. Okay, nothing much under x-axis, x, y. Okay, so from here you can guess that here what you will see is this point is 1. Okay, so that's why this doesn't give you any idea. When you look at here, you see that the horizontal asymptote is 3. So this is our asymptote 3. And somewhere around, if this is 3, so somewhere around minus 500. So I'll draw this not to scale. So this is approximately minus 500. Actually, this is minus 499 point something. You have a vertical asymptote. Okay, this thing vanishes on that part. That's why this doesn't see it, because it's just doing it for some numbers here. So the graph is actually like this. It comes here. Okay, so it comes like this, comes like this. It's okay, like this, and then goes like this. So you see what the computer did was, so this is around 1 here. Okay, so the computer gave you only this piece. Okay, and this is what is happening outside that piece. And in order to see this picture, you have to actually do these things. Obviously not by hand, but you have to calculate those roots, approximate the roots, examine the signs, etc. Okay, so this was a nice example from the book to warn you to be careful. Okay, thank you. That's all for today.